not seeing your charts. Oh, why are we recording? Okay, we're recording it, huh? Okay. Yeah, go on full screen, huh?
Can you shift this?
Hit this.
What is this for?
Project it.
No, this is.
Okay.
Hey guys, only one guy should have audio. Don't everybody should not have audio.
Only Sujoy.
Just move to the...
Okay.
That's the record now. Okay. Everyone can hear me. Professor, you can hear me, right?
I can hear you. Can you switch screens or whatever?
Which screens?
Yeah, because now I'm seeing the little thing. I'm seeing your I'm not seeing the full screen view.
Oh, okay.
Just present.
You need to do that.
Yeah, just do mirror the display. That should be enough.
I think it's presentation showing up like this.
Okay. End the show. And then just go slideshow.
Right.
Oh,
No.
Yeah.
No. Yeah, that's better. Good. I see it. Okay,
Yeah, but
awesome.
here-
Let's go, Gautam.
Yeah. So hello everyone. So today I wanna go over basically some fundamental physics of magnetic materials, on-chip inductors, and also talk about how we can make very good magnetic inductors and transformers, and also what are the various challenges in actually making them. Okay. So first thing is, so what exactly is an inductor? So an inductor is basically a device that stores magnetic field energy. And by doing that, what it does is it actually, when you have an inductor and you apply a time varying current through the inductor, it has an induced voltage that opposes the applied current. So that's the fundamental of an inductor. So in order to find the inductance of any coil with some magnetic material in it or even air, is the inductance is just the number of turns in the coil times the flux linkage through the coil over the current that is passed through the coil, right? There's also another way to define inductance, which is in terms of energy. So the energy per unit volume stored in the magnetic material is basically 1 over 2 mu naught B square. And so if you just, and because the energy stored in inductor is also half Li square, if you equate both of them, you can also define inductance in terms of the energy density in the field. So what this tells you is that in order to increase inductance, you basically need to find a way to increase the magnetic flux density throughout a volume of space. And this is also the fundamental reason why inductors don't scale like capacitors. So in a capacitor, you can scale down a capacitor, you can increase the capacitance density just by bringing the two plates close to each other, increasing the area, and then basically crumpling it up into a suitable form factor, right? Like that's what you do in a deep trench capacitor. So you take a large sheet, you reduce the thickness between the plates, and then you basically push that plate essentially into a hole so that now you have this over a smaller effective area, right? So that's what you do in a capacitor. But in an inductor, that's fundamentally not possible because in order to increase the inductance, you need to increase the magnetic flux density per unit volume. So it scales actually with volume versus area. And therefore, you can't make an inductor. That's the reason why on-chip inductors are not even close to as good as on-chip capacitors. So that's the fundamental reason. So when you talk about coil geometry, right? So a lot of, I think during my master's, a lot of work went into understanding, so given I have a conductor, like a loop of wire, is there some way of having a loop, an optimal way of having a loop that increases the inductance density, right? But it turns out that no matter what complicated shape of a loop you make, what happens is one side, so imagine you had some random loop, right? That's like just randomly looping around. What happens is that some of the loops that go in one way cancel out with the other way. And what ends up happening is that there are only certain possible ways that are the most optimal ways to make an inductor in terms of coil geometry. So if you're talking about a 2D geometry, right? So there are all these possibilities. There's a line, circular spiral, square spiral, and racetrack. And we'll talk a little bit more why the racetrack is particularly very important. And then there is a 2.5D approach, which is essentially you have multiple two-dimensional levels, but the two-dimensional levels are connected through a via. So then you can make essentially a three-dimensional inductor, but it's not truly three-dimensional because in one of the dimensions it's just restricted to a via. And the
Yeah,
third
and
one,
Gautam, I should mention here, this is the correct use of the word 2.5D because it's not referring to an interposer. It's pseudo 3D, right?
yeah, correct. Yeah. Yeah, and the third important kind of geometry is just the overall three-dimensional geometry, right? And when you do three-dimensional geometry, there are only two possible ways you can do this. One is to just have a solenoid, and the other one is to wrap the solenoid around itself to create a toroid. And if you look at all these possible ways to make an inductor, the toroid actually can have the highest inductance density because it has both a three-dimensional structure with large number of turns, but also it loops around itself, so it amplifies the overall flux in the core. So that's the first consideration. Right? So I'm going to talk about all the considerations you would think about in order to make an inductor. So the first one is the coil geometry. The second important consideration is the choice of the magnetic material, right? And in order to understand the choice of the magnetic material, you need to understand where does permeability actually come from, right? What is the origin of permeability? So fundamentally, what happens is when you take any solid, so a solid consists of a lot of atoms which are basically bonded to each other. And in these atoms, usually in the outermost shell, there is usually an electron, and that electron has a spin. So in certain elements, what happens is there is a certain kind of interaction in fundamental quantum mechanics called exchange interaction, which is when two atoms are placed very close to each other, because so if you consider everyone knows what is distinguishable and indistinguishable particles, right? So if I take two particles just like this, classical particles, they are distinguishable because I can assign a label to this particle as this is A and this is B, and I can track each particle individually. But in quantum mechanics, fundamentally, you cannot do that. Every electron is identical to the other electron, and you cannot fundamentally distinguish one electron from the other, right? So when you write any wave function, you have to write it in a form so that even if you exchange the particles, the wave function takes the same form, okay? And so in order to do that, and that process of saying that the Hamiltonian, which is the energy term in quantum mechanics, doesn't change with the exchange of the electrons, that is called as exchange interaction. So when you have these multiple spins which are very close to each other, you can write a Hamiltonian in this way. This is called as the Heisenberg Hamiltonian. And what this is essentially saying is that let's consider two electrons I and J. So let's say the ith electron has a spin Si and jth electron has Sj. Then what you do is you take the dot product of the two spins and multiply it by something called as an exchange integral, which really depends on the crystal structure, how far those two electrons are located, and so on. And then you sum it over all possible nearest neighbors. So I and J correspond to all possible nearest neighbors of the spin, right? And if you actually do the quantum mechanical simulation of the crystal structure and the electronic configuration, what you'll find is that this exchange integral term Jij can be either positive or negative depending on the crystal structure and depending on the solid. So if Jij is positive, so if the exchange integral is greater than 0, what that means is that if Si and Sj are in the same direction, right? And if Jij is greater than 0, then the overall term is positive. And because the Hamiltonian has a negative, that means the overall energy is reduced, correct? So if your exchange integral is positive, then you have two spins trying to align in parallel with each other. And then you get so-called ferromagnetic order. However, if the exchange integral is negative, then you have a situation where the two spins next to each other have to be anti-parallel so that they can reduce the overall energy, right? Because only if this is negative, this dot product has to be negative, so that overall the Hamiltonian is negative and the energy reduces, right? So that's how you get the ferromagnetic and anti-ferromagnetic order. So in the ferromagnetic order, basically the exchange integral is positive. In anti-ferromagnetic order, the exchange integral is negative. So you have anti-parallel order. And this exchange integral, depending on its magnitude, right? In some cases, the magnitude of the exchange integral is very less, and then you don't get a ferromagnetic material, but you get a paramagnetic material. So it still shows some magnetic behavior, but it's not as strong as a ferromagnetic material. And finally, you have another class which is called as ferrimagnetic ordering, which is what you find in ferrites. So what actually happens in ferrites is you have some kind of a ceramic structure, and you have so you have two sets of, let's consider two sets of atoms, okay? And these atoms occupy two different interstices in the crystal. So there's the octahedral interstice and a tetrahedral interstice. So all the atoms in the tetrahedral interstice undergo exchange interactions with each other, and all of them in octahedral interstices undergo exchange interactions with each other, and they are separate. But depending on the exchange integral of each one of these exchanges, what happens is they essentially align in parallel. Each interstice is individually ferromagnetically coupled, but two different interstices are antiferromagnetically coupled. So what happens is some of the octahedral electrons all align in one direction, the tetrahedral electrons all align in another direction, and they oppose each other. So overall, even though you may have ferromagnetic ordering because one of them is stronger than the other, the net effect is that one cancels the other, so it's not as strong as a ferromagnetic. That makes sense, right? So any questions?
Maybe some like brief simple way tell that exchange interaction thing, like what exactly?
Okay, so what happens is, imagine you had, and
Why does it happen?
no, it happens because electrons are not distinguishable, okay? So imagine I had a two electron system, right? If I write a wave, so imagine I had one electron, actually I can write on the board. So imagine I had so imagine I had two atoms, right? And say this had some kind of a cloud and this had some kind of a cloud, right? And say they were kind of interacting with each other, right? So the wave function of the electron here is some psi 1 as a function of R1, right? Where R1 is the coordinate of the first electron, right? And this electron has a wave function psi 2 of R2, right? So what happens is if I take this entire system as a whole and write the wave function as psi equals some combination of these two, because you cannot distinguish one from the other, this wave function needs to have a functional form that if I replace R1 with R2 or R2 with R1, if I exchange the electrons, right, the wave function should not change its form.
That not that bad. Like why should it occur? Like why in specific these materials occur, not in others?
Why? Oh, that depends on okay, that really depends on the chemistry of the electron configuration and how the electrons interact with each other. That's why it happens only in certain materials. Like why, for example, semiconductor, silicon is usually, I think, diamagnetic, right? It's most materials are diamagnetic, right? They're not ferromagnetic. It's because when you actually consider the crystal structure as well as the outermost shell of the electron, the exchange interaction integral is very small. So they don't couple as much. So these are called as highly coupled materials, right? So the spins next to each other highly coupled with each other. So that's what gives you that ferromagnetic. And that's really a fundamental property of the chemistry of the elements that make up that crystal. Right? Yeah. And so, and this is very interesting. So now that we understood like how magnetic ordering happens, right? So what is the fundamental reason why domains happen, right? So when you consider any ferromagnetic material, there's domains, right? So the reason that domains happen is really because of a statistical phenomenon. So what happens is not only is the energy, so the Hamiltonian is given by this, but not only does each spin have an energy, each electron have an energy, but there's also a statistical process. So there's some distribution of them, right? So depending on the energy it has and depending on the temperature, there's a certain probability that an electron occupies that state, right? And usually you can consider, for example, that as Boltzmann statistics, right? So for example, if I write the energy as something like this, which is the Heisenberg Hamiltonian, then if you know from fundamental quantum mechanics, right, if this is the energy term, then the energy eigenfunction, the energy eigenvalue, right, the actual energy of the electron, if say the ith electron has a wave function psi I, right, then the energy of the ith electron would just be taking the inner product of h psi I with psi I. That's the energy, right? And so the probability that the ith electron will be in the state psi I at a given temperature would therefore be given by the Boltzmann distribution, correct? So what that means is that when you have high temperature, even though you have magnetic ordering, because of the high temperature and Boltzmann statistics, most of the electrons will tend to randomly orient with each other. They won't tend to kind of condense into one ordering, right? So if you combine this Heisenberg Hamiltonian with the fact that there's a temperature distribution, and say you sweep the temperature, so this is an actual simulation showing how domains form, okay? So each dot here is a different electron, so it's simulating a different electron, which is coupling with the adjacent lattice point. And so it has a Hamiltonian, but simultaneously you are reducing the temperature from very high to say room temperature, right? So initially when you start, everything is random, but as you lower the temperature, you see how they condense locally into regions. And these are what you call as domains. That makes sense. Any questions? So the domain structure really happens because there is this exchange interaction coupled with thermodynamics and statistics of how these things exist in those states, depending on the energy and depending on the temperature, right? And this is actually a very fundamental concept. This is called Ising model, and it's not only applicable for magnetism, it's actually applicable for any kind of system where you have multiple things that are interacting with each other. It could be anything. So one of the very interesting models I read once was like trying to model how thoughts come in the brain itself using an Ising model. So initially you have a whole bunch of neurons, and there's a certain equation that describes how one neuron interacts with the next neuron. And initially all neurons are randomly oriented, which means you're not thinking anything. But then over time, they all condense and create regions like this, which means those neurons are firing together. And that's how, the brain, for example, operates, right? So this is a very fundamental model that talks about how a collective combination of different things, each having an interaction with each other, behave when you incorporate statistics into it. So now that you understand, like, for example, how the magnetic ordering happens and how domains form, right? The next important concept is what happens in the dynamics of this. So imagine now you have this kind of magnetic ordering, domains have formed, but now imagine I apply a field, but I'm varying the field with time, right? How does the magnetic domains and how does the magnetization change with time? So this is a very complicated equation, actually. It tells you how, as you apply a magnetic field and as you're varying the magnetic field with time, how does the magnetization in the material actually change with time? Okay. So actually, the way this works is like, so imagine you had some kind of domain structure, right? So imagine you had all spins in this direction. Imagine I applied a field in this direction, right? So what happens is this spin now tries to align in this direction, and that's the first term. So M cross H, because this field exerts a torque on the spin, right? And torque is, so if this magnetic moment is M and this is the applied field H, then the torque that tries to move this is M cross H, right? So the change in magnetization with time is equal to, the first term represents how the torque moves the magnetization. The second term has to do with the fact that when you apply this field, it just doesn't go immediately to that direction. But what actually happens is it kind of precesses about the applied field. Okay, so imagine you had a spin like this, and then I applied a H field this way. It tries to come in the direction of the applied field because of the torque. But as it does, what actually happens is it kind of rotates around it and precesses like a top, and then it comes to zero, right? And in fact, this is how MRIs work. So when you go in and when you take an MRI scan, right? So you have this Helmholtz curve that aligns all your hydrogen atoms in your body in water this way. And then if you've taken an MRI, they have another device there that applies microwave signals, and that causes these precessional movements. And from that, it generates the image of the body. Okay. So this is called NMR. It's called nuclear magnetic resonance, right? In this case, it's just magnetic resonance, but in that case, it's nuclear magnetic resonance. But yeah, so this precession is there. And what you can do is you can actually, this equation here depends on the torque and also depends on this so-called precessional moment and damping. And this field that the spin actually experiences, it's actually not just the applied field. It's something called as the effective field. As we will see, inside the crystal itself, there's a built-in magnetic field intensity as well, depending on the crystal structure as well as the shape of the magnetic film. And so the overall field is a sum of this magnetocrystalline anisotropy, which is the HK, the shape-induced magnetic field intensity, which is the third term here, and the applied field. Okay. And so now that you have this dynamical equation that describes how the moments change as a function of time with the applied field, if you now use a time-varying applied field, right? Imagine you applied a sinusoidal field, then you can actually calculate that there's a certain cutoff frequency for the response of the moment to the applied field, okay? And that's called as the FMR frequency, and that is given by this term. And you can also calculate, given that the frequency is zero and the DC condition, what the permeability is, right? So if you take these dynamical equations, assume a time harmonic applied field, and then plot what is the behavior of the permeability as a function of frequency, what you find is that the permeability remains constant up to a certain point, and then it starts to roll off. And that's the region where the field is moving so fast that the magnetic moments no longer can respond to it because they have this inertia, right? And usually when this permeability drops, there's also an increase in the loss. So that's why when mu r prime, the real part goes to zero, goes to one, basically behaves like air, then the imaginary part also goes up because the loss also goes up. Okay, because that's basically the definition of resonance, right? When you have a resonance, your permeability goes down, but the loss goes up, right? And here, if you look at these two equations showing the cutoff frequency as well as the DC permeability, you can find a fundamental relation between the two. So if I just take these two equations and substitute one in the other, you'll find that the DC permeability is inversely proportional to the square of the cutoff frequency. So if you have a magnetic material that can operate at a higher frequency, that can go up to a higher frequency, naturally it tends to have a lower DC permeability. Okay, so there's this inherent kind of compromise between how permeable a magnetic material can be versus how much frequency it can actually operate at. Okay, and this is called as the Steinmetz equation. Yeah, so now if you remember in this equation, right? So in the previous dynamical equation that was shown here, this field that you apply, the field that the spin actually experiences is actually an effective field. So it's a sum of the applied field, a magnetocrystalline field, as well as a shape field, right? So how do those fields actually come? So what happens is, here is an example for iron, nickel, and cobalt. So what they do is they do basically a quantum mechanical simulation to see if I have a spin in a particular direction in a crystal, and I rotate that particular spin, say three-dimensional, right, in theta, in the theta as well as phi in a sphere. What happens is there's an energy landscape for the orientation of the spin, okay? What it means is that certain directions are more preferable than others in the crystal because certain directions have a lower energy as compared to others, okay? So now what that means is that imagine your spin was oriented in one of these low energy directions, right? If you try to push it a little bit closer to the high energy direction, then you will get a field, built-in field that opposes that because of the energy landscape, right? So that is this magnetocrystalline anisotropy field, HK. Similarly, you also have another phenomenon which is called as a shape effect, which is depending on how your film is patterned. So if your film is patterned this way, for example, you can see here on the right. So if the magnetization is done in the direction of the long-sided direction, it basically creates more magnetic charge at the surface and it opposes the magnetization more. So it tends to be more difficult to magnetize along the long direction versus a short direction. And so you have this so-called hard axis as well as easy axis of magnetization, right? So the consequence of these is that, so for example, you can see in the shape anisotropy, if I were to magnetize this film in this direction and plot what is the, for example, the hysteresis curve, you'll see that in the easy direction, it tends to magnetize much faster because you can see with the applied field, the magnetization increases very quickly, which means the material saturates much faster. However, if you were to magnetize it along the hard direction, which is in this direction, you see that it takes a much larger field to saturate the magnetization, right? So you have this fundamental kind of hard axis and easy axis of magnetization inside the material. And you also have this magnetocrystalline effect, which you can see how with the applied field versus the magnetization, in different crystal directions, you have a different amount of magnetization, depending on how easy it is to magnetize in that direction, right? Yeah. And here, this is just a kind of an overview of different kinds of magnetic materials you have, usually plotted as the permeability versus the saturation field. So you can see you have basically metal and alloy ferromagnetic materials. They have the best performance in terms of permeability as well as in terms of the saturation field. And then you have ferrites, which have a much lower permeability, and they also have a lower saturation field. But ferrites have a very important advantage, which is that they are resistive materials. So if you're making an inductor with a ferrite, you don't have to laminate it like how you laminate a transformer because it has a high resistivity. So even if you use the bulk material, the eddy currents are very less, so the losses in the inductor are less. So really the choice of material depends a lot on your fabrication complexity. If you go for a ferromagnetic, you can get better behavior in terms of permeability and saturation field as well as frequency, but then you will have to laminate the material. And sometimes doing laminations on chip is very difficult. But if you use ferrites, you don't have to laminate, but then it doesn't go to very high frequencies. It also has a lower saturation field and a lower permeability.
When you say it doesn't go to high frequency,
Yeah.
what's the range of frequency we are talking about?
So ferrites usually are chosen for like 100 megahertz, up to 10s to hundreds of megahertz.
Very low.
Yeah, but ferromagnetic can even go to gigahertz plus. Okay, yeah.
So this chart,
Uh-huh.
B saturation, that's in Tesla, right? Unit is Tesla.
Yeah.
So 2 Tesla, and it's not frequency dependent, the saturation.
Saturation is not no, the saturation is frequency dependent.
Yeah. So what about in this chart?
Oh, you mean BSAT
Yeah.
is BSAT is not BSAT. Okay, BSAT and saturation magnetic field and magnetic the saturation magnetization, right?
Yeah.
They only depend on the number of spins per unit volume.
I see.
Because imagine all of them are aligned, right? So what's the maximum magnetization you can get, right? But the amount of current that gets you to the saturation depends on the material, because if the material has a higher frequency of operation, right? Then if you remember the Steinmetz equation, it naturally has a lower permeability. So that means it can support a higher current before all the spins align because it has a lower permeability, right? So higher frequency means it will have a higher saturation current.
So there's
So-
one point I want to make here, Gautam, and maybe you can elaborate a little bit more. So, on this curve, we've always assumed that there's some material there. One can also have a magnetic field in free space. Okay? And there are presumably no electrons.
Yeah,
right?
yeah.
And so that's a very special case in which there is the field, okay, and the magnetization are linearly related to each other, right? BH is a linear curve. There is no frequency dependence, okay, and there is no saturation, okay. So you may want to talk one sentence about that.
Yeah, If if you didn't have any magnetic material, then your permeability is going to be 1. And you can apply any amount of magnetic field and obviously it won't saturate and it can go to any frequency, right? But the only caveat is that when you do that, because your permeability is 1, in order to get the inductance, for example, a certain value of inductance, you need basically a large area or a large size of your inductor, right? So it's really a compromise between your losses, frequency, and inductance. And I'll talk later, just so you have many kind of things that oppose each other, okay? One of the things that opposes is the frequency operation in mu r, which I talked about, right? There's also another kind of opposing factors, which is the inductance density and the quality factor. So generally, when you make an inductor that has a higher density, it tends to have a lower quality factor and vice versa, right? That's why air core inductors have very high quality factor. You can even get 100, but they have very low inductance density. But if you take a magnetic core inductor, it can have very high inductance density, like sometimes even 1,000 nanohenries per square millimeter, but then its quality factor would be like 5 or something like that, right? Because there's again an inverse relation between the two, between the loss as well as the inductance density. And so imagine you were, and I think here is really where a lot of research is, at least in on-chip magnetic inductors, is missing, because a lot of people who do on-chip magnetic inductors research in engineering, right? For example, in packaging and so on, they are not physicists. So they don't really fully appreciate the physics problem here. They only look at it from an engineering perspective, right? But I think you need a lot of research where you have a combination of a physics perspective of looking at this problem with an engineering perspective. So how would something like that look like, right? So I'll talk a little bit more later about what I think the future of this kind of research should look like. But fundamentally, right, all these magnetic processes like calculating permeability, frequency, and all can all be simulated in a computer, right? So you can take this Hamiltonian, you can run very complex simulations of the atomic structure to figure out the magnetocrystalline anisotropy, the exchange integrals, and so on. And there are very sophisticated tools already available. For example, this is a tool I've used before from NUMAC. It's a tool from NIST. And what this tool can do is if you input the exchange integral values for nearest neighbors as well as the magnetocrystalline anisotropy, and then depending on what shape of the film you draw, it can actually kind of simulate what the domain structure would be. So for example, here it's assuming spins distributed throughout, and it's simulating in this particular structure how these spins will be because of the exchange integral as well as the temperature, how the spins would align, and it gives you some kind of a domain structure, right? And from this, you can calculate what the permeability of this would be. Similarly, you can also, in the software, you can also apply an external field, and you can simulate how the domains change and how your field also, your magnetic B also changes, right? And also, if you see a lot of ferromagnetic materials, people have initially tried nickel and cobalt and nickel iron, but there's a lot of research has been looking at using alloy kind of metals and cobalt, zirconium, tantalum or something, right? And it turns out that alloy ferromagnetic materials can have a high permeability, high frequency operation, and also have a high resistivity, right? So there's also a lot of research need to be done in material science to figure out new kind of ferromagnetic materials that are better than the ones we currently use. So the next important consideration is the topology, right? Right now, till now we've talked about magnetic materials, and now let's talk about the actual topology of incorporating a material, right? So imagine consider a simple case, you just have a loop of wire which is carrying a current, right? So what are the possible ways that you can place a magnetic material, right? So one is you can cover the entire region around the coil, so it covers everything, right? And then you have this the second approach, which is to have a central core, and then everything else is empty. Then you can have a toroidal core that just covers the coil, the wire itself, but then it has a hole in the middle. And then you have a final approach, which is there's a central core, and then it wraps around the coil. So these are the four possible geometric ways you can actually put a core around a coil, right? And if you use this very simple kind of a thing, and then you simulate what the inductance would be. So here I've plotted the inductance, the ratio of the inductance of each one of these kind of possibilities versus over the inductance when the magnetic materials is throughout the volume, right? So obviously this would be one because it's the same thing. But what you find is that if you go to something like this, the second approach, where you have a magnetic core in the center, which is kind of cut out like this, it actually has a non-negligible inductance enhancement. In fact, it behaves like air. And the reason why is because most of this region is still surrounded by air. And so if you calculate the reluctance, right, which is basically an analog of resistance, even though in the center you have magnetic material, when you close the loop, most of the reluctance is dominated by the air in between, right? So this ends up behaving as if the material wasn't even there, most, right? And so the best approach, right? The best approach is when the magnetic material creates a loop around the coil and completes that loop as close to the coil surface as possible. So that's why this approach, where the magnetic material is around this loop of wire and very close to the surface of the loop, and also in this case have the highest inductance, right? Versus a case where the material was far away from the central loop, as well as a case where it was just open at the sides. So you need to place a material so that it's very close to the surface of the coil and also completes the turn around the coil. Okay. The other thing is, when you talk about ferromagnetic materials, you also need to consider how the bulk of the material has to be, right? Because you cannot use one large volume of material because then your eddy current losses would kill the behavior of the inductor. So you have to break it up into pieces, right? So what are the different ways you can do it? You can break up the magnetic material into basically like regions, like dots, for example, here. Or you can have kind of wires of magnetic material oriented in different ways. Or you can have sheets, right? And if you plot the effective permeability of this kind of a volume as a function of the packing fraction of the magnetic material, what do you find that in the case of when you use dots, right? So for example, if you use like microparticles of ferromagnetic material, you need to get almost a fill fraction close to like 95% or plus to see any improvement in permeability, because it's mostly dominated by the air gap in between, right? So initially when I was doing my master's, we were looking at using cobalt nanoparticles to make the basically the core of the inductor, right? So there, the idea was you would mix these cobalt nanoparticles in SU8, and then you would spin coat the SU8 so that you have a magnetic film that is spin coatable. But the problem there was that in order to spin coat something like that, you cannot obviously use 100% fill fraction, right? You need to use you can use like maybe 50%, 70%, right? But when you use that, you get non-negligible improvement in the permeability. So it's as if you don't even do it, right? So that was the main problem in that particular project. And so if you look at this, the best approach would be just to use sheets separated by an insulator, just traditional lamination, because when you do that, depending on fill fraction, there's just a linear increase in the permeability, right? So now I'm going to give you an exercise. Okay. So how do you combine all the four approaches we've talked about, right? So imagine I'm combining this. I need laminations. Then I combine this. You need the magnetic material close to the surface and surrounding the wire, as well as combining, ferromagnetic material with coil geometry, right? So I'm going to give you an exercise. How do you combine all these things, all these different concepts we learned so far, and make an inductor that can be used on chip? And if you understand why this is the case, you'll understand why most of the research is done only in one kind of inductor. Okay. And that's the most popular research that's been done on-chip. So here's the thing, right? So from the first thing we talked about, if you want to fabricate this on chip, you need to go for a 2D geometry because that's the easiest to do, right? And so if you go for a 2D geometry with a racetrack kind of a geometry, and then explain why the racetrack is needed, combine that with a high permeability ferromagnetic film. And for example, cobalt zirconium tantalum is one option. It has a high permeability, but it also has a high uniaxial anisotropy, which means you can actually grow that film in the presence of a field. So it actually has an anisotropy field built into it, depending on the way it's grown, so that if you now magnetize in the direction of the hard axis of that particular film, you can push the frequency of operation much higher, okay? And that's really why the racetrack is needed, because if you use a racetrack, then what happens if you look at how the field is distributed, in the long end of the racetrack, the field is essentially just perpendicular to the conductor direction, right? So if you grow your magnetic material so that this direction is the hard axis direction, then you can make a magnetic material that have high saturation as well as high frequency operation, right? So if you combine the 2D racetrack plus high permeability material, plus have the magnetic material in such a way that it essentially is as close to the conductor as possible and wraps around, plus use laminations, right? So combining everything we learned so far, and that's where you get the most popular inductor in literature, which is the racetrack inductor, okay? So here you see the racetrack inductor here, and if you look at a cross section in this direction, right, you see how these are the inductor wires, and just like how we talked about, there's essentially the magnetic material going around around the conductor, right, as close to it as possible. And this is really limited by processing conditions, right? So here, and also if you notice, they've grown this for a ferromagnetic material in such a way that this direction in which the field would basically rotate around the coil, around the conductor, is along the hard axis of magnetization, so that you can push the frequency as well as the saturation field, right? And so you have the current is going into the plane over here, and then you have this magnetic material on top and bottom, and then the loop is completed with this magnetic via, which is just essentially two films touching each other. Okay. And here you see this is a plot of various different inductors reported in literature, on-chip inductors. So it's a plot of the inductance density in nanohenries per square millimeter versus the quality factor, right? And so this particular work, the racetrack inductor, has the highest inductance density. So it has nearly 1,800 nanohenries per square millimeter. However, because it's a two-dimensional surface, right, and you have a large number of turns, and this thing is very small, it has a high loss. So it has a high resistance, right? So that's why even though it has a high inductance density, its quality factor is only around 5. And you notice that there's a general trend that you see all these different kinds of inductors and geometries people have tried. As they actually have a lower inductance density, they tend to have a higher quality factor, okay? So there's really a fundamental kind of imaginary line that exists, which is, if you know from basic optimization, it's called a Pareto-optimal behavior, where two different parameters inversely affect each other, okay? And so there is some surface somewhere that you cannot cross. And the way you cross it, the only way to cross it is to have an innovation in magnetic materials, okay? So this problem is, that's why the on-chip inductor, in my opinion, is failing, because people are looking at it only from an engineering perspective. Because the physicists are not interested in making an on-chip inductor, because they have better things to do, right? So you need someone else to come in and combine both these things, because you need someone with expertise in physics and physics-based modeling, as well as some processing experience, some engineering experience to actually integrate, right? And so, we talked so far about inductance density. So what are the various loss mechanisms? So, losses in inductors, there are many different loss mechanisms. So there's one which is called as proximity effect, which is basically, imagine you have two loops of a conductor carrying a current, right? So the inside loop generates, so basically imagine the outside loop is generating a field. That time varying field is cutting through this conductor, and that induces basically a voltage in the conductor that opposes this current, so that the current tends to crowd more towards the inner surface or the inner edge of the conductor, right? And so effectively the cross-sectional area of the conductor is now reduced. So its resistance has gone up, right? So this proximity effect, which again depends on the rate of change of magnetic field and hence the frequency, is basically causing an increase in the effective resistance of the conductor. And then the second thing is, very familiar, is the skin effect, which is very similar to this phenomena. You have a time varying current generating a field. The field is inducing a voltage inside the conductor itself, and that voltage, because of Lenz's law, opposes the current in such a way that the current tends to crowd more towards the edge of the conductor. And so as you go to higher and higher frequency, you tend to have this current crowding more towards the edge. So the effective cross-section area of the conductor is reducing, and hence the loss is going up, right? And then you have, of course, in the magnetic material itself, you have something called as hysteresis loss. And that really happens because of the second law of thermodynamics, which is that when you are changing energy from the field to the orientation of the spins, some amount of that energy has to go into heat. And that basically results in a situation where you have this, where the B and H have a kind of lag between each other. And so per cycle of magnetization, if you plot the BH curve, the area under the curve tells you per cycle of magnetization, how much energy is lost per unit volume of material, right? So this is basically the hysteresis loss. And the way you reduce this is you make the material as soft magnetic as possible, because if you make it soft magnetic, this so-called coercive field reduces, and so the area under the curve actually reduces per cycle. So that's again the reason why you use these ferromagnetic materials, soft ferromagnetic materials, because they have a very low area under this BH curve, right? And then the fourth loss is the eddy current loss as well as magnetic shielding. So eddy current loss, as you have this conductor, you have this time varying field, and the time varying field, because of Lenz's law and Faraday's law of induction, induces circulating currents in the magnetic material, which creates resistive losses. So you have some power loss there. And there's also a shielding effect. And what the shielding effect is when these eddy currents are actually created, they are also currents, right? So they also generate their own field, and that field opposes the applied field. So there's a combination of two effects. One is that there's a resistive loss in the material itself, and also the field that is going into the material is also reducing with frequency, which means that the material is becoming more and more like air, because the cross-section of the magnetic material itself that's supporting the field is reducing with frequency, right? So all these are frequency-dependent parameters. So basically with frequency, essentially what is happening is you have increase in resistance because of cross-section area change, increase in the number of cycles per second, and therefore increase in the hysteresis loss, as well as increase in eddy current loss, as well as magnetic shielding, which is reducing the permeability, right? And then finally, there's also this. This is not really a very important problem for power inductors. It's more a problem for RF inductors. There's also the fact that no inductor is an inductor by itself, right? It obviously has some parasitic capacitance. So what happens is, beyond a certain frequency, which is the resonant frequency of this LC network, this no longer behaves like an inductor, it starts behaving like a capacitor, right? So you want to always operate your inductor as far away from the self-resonant frequency as possible, right? This is usually not a problem for power inductors because the self-resonance frequency is so large compared to the usual frequency operation. But if you make inductors for RF applications, where you operate at like tens to hundreds of gigahertz, then the self-resonance is a very important factor. That's why if you look at very high frequency, very high frequency applications, people always use just a straight wire as an inductor, because a straight wire has the least self-resonance, right? The moment you start turning the inductor, turning the coil, the wire to make an inductor, you have capacitance coupling between two adjacent turns, and then that increases your capacitance. So again, emphasizing this fact that there's a fundamental kind of a limitation, kind of an optimization that has to be done, because the inductance density and the quality factor oppose each other. And there is some imaginary line somewhere that people haven't really looked at this very well, but there is a line, and the only way to break that line is to have innovations in magnetic materials, right? So to conclude, right? So what I think the future of this should be is we need to use some kind of physics-based models with emerging AI, machine learning, whatever, to kind of predict new materials, new combination of different kinds of alloy paramagnetic materials that have a higher permeability, higher resistivity, higher saturation, as well as frequency operation, right? And this really comes down to trying different combinations because experimentally you can only try so much, right? And I think this field can borrow a lot from what people are doing with high temperature superconductors. So in a lot of the high temperature superconductor research, people are using machine learning actually to predict different kinds of combination of elements and crystal structures to push the critical temperature of the superconductor higher, right? But that kind of approach hasn't been applied to magnetic materials yet for this kind of application. So applying that kind of research to something like this, obviously, which needs very specialized expertise to do, would help in predicting new kind of materials that can have these kind of benefits, right? So use physics models to predict new materials, then use micromagnetic simulations to optimize the film geometry as well as structure. So by doing that, you optimize the built-in field so you can push the frequency and so on. Then choose optimal 3D coils. And here's where a lot of this kind of inverse design concepts can come in because you have some targets and you can use basically kind of inverse design approaches to figure out what the optimal coil geometry would be, right? And then you basically do this entire optimization to figure out what is the best optimal inductor with the material that you have designed, as well as with the coil geometry and so on, right? So I think this is where this kind of research should go to, but I think this really needs a lot of expertise in many different fields. It just can't be done just by, electroplating a material, putting a coil, and just measuring the inductance, right?
Good. Thanks, Gautam. Yeah. So, you're going to go to transformers now. Okay. Hey, I have to leave now, but Sujay, you're recording this, correct?
Yeah, I'm recording it. Yeah.
Okay. Okay. So, how much more do you have, Gautam?
Actually, this transformer slides you've already seen. They're the ones I sent you.
Oh, okay. Okay. So, I just want to put a little editorial component, right? Why have I asked Gautam to sort of study this problem? Does anybody know? And don't say he has nothing else to do, okay?
Or
Anybody?
backside,
Huh?
backside of theory using transformer.
Why? Why are we interested in transformers?
We want to increase the power conversion efficiency.
Okay, so again, right? I mean, a lot of this, I mean, has to go back to the early days of electricity. All right. And there were two towering personalities in the field of electric transmission and conversion. One was a guy called Nikolai Tesla, and the other guy was Edison, right? And they had a big war going on at that time called the AC-DC war. Okay. And it is not the Metallica band of today. Okay. This was a genuine big problem that these two guys and they were all, and Tesla sort of made his mission to do power transmission by AC and at high voltage, right? And in fact, he set up a whole thing to transmit power from Niagara Falls to the city of Buffalo using high voltage AC. On the other hand, Edison, right, had already invested a lot in DC power for his lights to power New York City. And so he, made a big stink about how AC was unsafe. Okay. And in fact, he electrocuted like animals to show that this was unsafe, but it was all a big charade. Okay. And he tried to push this DC power transmission, but DC power transmission could not go very far. Okay. Because it's very difficult to up convert and low convert DC voltages, right? Because as we know now, right, as we are trying to do this in our own packaging, right? But AC is very easy to do with transformers, okay? And so basically, at the end of the day, right, Tesla won, but not when he was unfortunately he didn't live to benefit from it. And in the meantime, our man Edison, who was a very good businessman, kind of, made the best of it and, made a lot of money. And, that was what happened. And that was the start of the company, which is called GE, General Electric. Okay, so General Electric actually was a company that Edison started to kind of leverage all this DC power transmission, electric lamps, blah, 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 right? And Western Electric, which was another company based in Philadelphia, in Pittsburgh actually, decided to back Tesla. Okay, and so they were the pushers of AC power generation and all that stuff. Yeah, and so in the end, Tesla won. So the reason I got kind of interested in this is over the last summer, right? I was when I had nothing better to do, I started to read the biographies of Tesla and Edison and all the stuff, and it suddenly occurred to me that we are doing power delivery to a package all wrong. Okay, and we should be following Tesla rather than Edison. And so then, I went into these whole transformers, and we had a lot of discussions with Gautam when he came back, and we're still struggling with how to build a good transformer. But I'm very convinced, right, that if we can build a good transformer, we can really change the way we do power delivery for our high performance packaging, right? And so that is the reason I want to kind of look at this problem more. And as as Gautam has said, it's a very difficult problem, and especially because it requires sort of it has too many dimensions in it, right? And one of which is the whole materials dimension. But it's not just pure materials, it's also how you synthesize these materials, how you wind the transformer, how you do all these things, and how you make the transformer small. What we're really talking about here are micro transformers, okay, that can deliver the power to the chips on a segmented basis. So maybe and this is actually the topic of my talk today, tomorrow at this conference, okay. And so maybe at some point, right, I'll record the talk and you guys can listen to it. But it's actually a very, I think it's a, if we can pull this off, it's a big deal, okay. So Gautam, keep up the good work and tell them about how we're going to build the transformer.
Okay. All right. Thanks, Rose. So yeah, I'll continue here. Yeah, so now let's look at, we talked so far about inductors, so now let's look at on-chip on-chip transformers for power delivery, right? So like as Professor mentioned, right, the way that power distribution is done today is you have some power plant and which generates, some voltage with a generator, and then you step up that voltage to very high voltages, like around 200 kilovolts or something like that. And the reason you do that is by using a very high transmission voltage, you're reducing the current. So you're reducing the I square R losses, the ohmic losses, as well as the voltage drop. And then finally, near the point of load, right? So the point of load here is maybe, this is like maybe Los Angeles. And the way you go nearest to the location where you need, and then you step it down from, and you can do this in multiple steps. So you can do 200 kV to like 11 kV, and then you bring the 11 kV as close as possible to your home, and then you step it down with a local kind of a transformer, a power transformer to like say 110 volt or something, and then you can use it in your home, right? And so there's this high voltage transmission that has multiple levels of conversion from a very high from first step up to a very high voltage and then step down all the way to 110, right? And these kind of distribution systems are actually very, very efficient. So typical kilovolt power transformers, step up and step down, are actually close to 99% efficient, okay? And overall, if you look at the power distribution efficiency in the US, it's around close to 90 to 95% efficient, okay? The distribution network itself.
When you say 95, you mean from the power plant to the point of load?
Yeah, from here to, yeah, from basically from where you generate the power all the way to the load, right? Yeah. But if you look at, okay, so one important thing is if you go and search what is the energy efficiency of US power grid, right? It'll say something like 30%. But that is because they are taking into account the efficiency of the power plant itself. The power plant is badly inefficient, okay, because the generators are not very efficient. And so like the efficiency here is less, but if you just consider the distribution part of it, right? The distribution and the power conversion, that's close to 90 to 95% efficient. And so, but however, if you look at the power distribution efficiency on a wafer, for example, a wafer scale system, right? It's only the best case scenario is only around 75 to 80%, right? State of the art. Why is that the case? So, fundamentally, the main reason is that, this is huge, right? And then when you make things much smaller, obviously the losses are going to increase because of the resistance of the metal wires as well as the frequency at which you operate, right? And also, when you do this, most of these kind of on-chip power distribution is happening with DC, and the only way you can convert DC from one voltage level to the other is to use nonlinear elements such as switches, right? Which are generally very inefficient. So the question is, can we use transformers instead of typical buck converters in order to distribute to a wafer scale system, right? And this is mainly work in progress, and I just want to talk about the approach that I've taken to particularly address this. And Namkang is the one who's going to work in the foreseeable future on this, maybe. But yeah. So why does frequency matter, right? So let me talk a little bit about why is the case that generally when your power density of any converter, this is not applicable only for transformers, this is applicable for even for buck converters. Why is it that when the power density goes up, the efficiency falls and vice versa, right? So imagine you had two power converters. So this is going to be a very hand-wavy argument, but I think it's a good way to understand this problem is, imagine you had two power converters, right? PC1 and PC2. So PC1, all these power converters fundamentally, whether you take a transformer or a buck converter, they are essentially converting energy from one form to the other. So in the case of the transformer, it's taking current in the coil, converting it into magnetic field, and then reconverting it at the secondary, right? In the case of a buck converter, it's sending basically the energy of the electron in the wire to a capacitor and inductor, basically what do you call that? Yeah, the bank. And then it's converting that into electrostatic field as well as magnetic field, and then reconverting it back into the energy of the current in the wire, right? So they have some kind of a conversion of energy happening at some frequency. And so in both cases, right? So in power converter 1 and power converter 2, let's assume that you want to be able to supply the same amount of energy, right? So imagine both of them have imagine that because of the size of this will be able to have a higher energy capacity as compared to this, just because it has a larger volume and larger area, right? So the energy capacity of power converter 1 will be higher than that of power converter 2. But how can you deliver the same amount of power, even though the energy is different, right? Because remember that power is energy per unit time, right? So if you want to deliver the same amount of power with a limited energy capacity, the only way you can do that is to do the cycling faster, because energy over time is the power, right? So essentially what this is telling you is that when you make the converter smaller and smaller and smaller, because the amount of energy the converter can handle at a given time, because the passives are getting smaller, is reducing, the only way you can deliver the same amount of power to your load is to do the cycling faster. So the frequency goes up. But however, when the frequency goes up, what happens is, one, because the energy is converting from, say, the current in the conductor to some kind of electrostatic or magnetic energy, there's obviously the second law of thermodynamics involved in energy conversion. So some amount of energy will be lost as heat. And also all the parasitics in the converter, such as the resistance of the wire and so on, also go up with frequency, right? So overall, you always tend to have this inverse relationship between the power density of the converter as well as the efficiency of it, right? Yeah. And so, like, in the case of the transformer, right? So what me and Namkang did over the past, I would say 6-7 months is to look at how we can optimize the transformer, right? And the way we sort of looked at this is to do like an analytic calculation of modeling of the transformer to figure out what are the equations that are involved. So here you see this is a typical transformer structure we consider with a bunch of magnetic materials with laminations, and this is the equivalent circuit of the transformer. Okay. So basically you have the resistance and inductance of the primary coil, and then you have, this is a resistance that's used to model the losses in the core of the magnetic core. And then you have this, basically this is where the transformation happens. So this is a coupled inductor. And then on the secondary side, you have its own resistance and inductance to model the parasitics of the secondary term, right? And so what you can do is using this equivalent circuit model, you can compute what is the primary current in terms of the secondary current as well as in terms of the other parameters of this equivalent circuit, right? And then not only is that, so the IE is a primary current which is drawn by the primary coil, but there's also a loss component of the current, and the loss component of the current is really going to depend on the hysteresis part as well as the eddy current part, okay? And so what we did is we took the total current, the input current is going to be the sum of the current drawn by the primary as well as the loss component of the current. And so what we are doing is we are starting from the load side and then we are calculating everything up to the source side, okay? So we start with assuming, say, the output is 1 volt, 1 amp. So say a chip that's operating at 1 volt, totally drawing 1 amp. So this is at a fixed load condition. And then you essentially back calculate all the other parameters. So you start with 1 volt, 1 amp, and then using this impedance, you calculate the voltage here, then the voltage here, and then you calculate the currents here, and then finally you calculate the input voltage, okay? And then you calculate the power density as the total output power delivered, which is, and remember, these are all phasors, right? They are not real numbers, right? So you have to take V times I complex conjugate, real part, and then you take the power density as well as the efficiency, and then we basically plot this. And so, this is like an overview of what kind of thing we did, because there are obviously a lot of parameters here. So what you need to do, like I mentioned briefly before, is you start from the output side and you slowly calculate everything by back propagating. And then what you do is for the transformer itself, there are various set of parameters it has. There are various geometric parameters, there are various core dimensional parameters and all that, as well as a material. And so what we did is you have this entire design space with all these different parameters, which we set ranges to, and then we did a Monte Carlo simulation. So we assume, so the only fixed values is the output voltage and current, and all other parameters were essentially swept across different ranges by considering different combinations.
What's
Okay?
the output voltage you assume? Why?
Yeah, I assumed one amp. Yeah. And so here is the result of, I think this was like around 100,000 different designs. And what you can see is a general trend. So this is a power density versus efficiency. And what you notice is that there's a general trend of behavior of this Monte Carlo, which is as you increase the efficiency, the power density is going down. But however, if you set your target as to have a transformer that has more than 1 watt per square millimeter, but simultaneously about 90% efficiency, there are some designs that satisfies this requirement. But if you look at the density of distribution, right? The density of distribution here is very less compared to here, which tells you that there's a very restricted number of designs that satisfy the requirement, right? And if you go and look at what kind of requirement it's needed, it again comes down to materials. So you need a material that in order to get this requirement for doing a direct 48 to 1 volt transformation, you need to have a magnetic material that has certain specs, like it needs to have permeability more than this, a certain resistivity and frequency operation, right? So again, this again comes down to the fact that in order to build a transformer that can reach the performance metrics you want, you again are looking at a materials problem. Unless you solve this materials problem, you cannot really cross this kind of invisible bound you have, okay? So that was the main conclusion from this. And again, this is a work in progress. So rather than doing a 48 to 1, right now we're looking at a 4 to 1, because 4 to 1 tends to be more efficient than a 48 to 1. So we are looking at that, but again, this is more work needs to be done here. But I think the fundamental idea you need to take from this chart is that there's always going to be this inverse relationship when you design, and to push the boundary of the design, you really need to do materials innovation with respect to transformers, right? And so what are, now that we talk about that, imagine you made this transformer, right? What are the ways you can integrate it? So for example, imagine you make this microtransformer as some chiplet, and then what you can do is you can essentially attach this chiplet to the back of, say, your SIF, and also attach other power converters and so on to it. So now you can have this backside power distribution network that's essentially AC, high voltage AC, and then it steps down over here and delivers the power to the individual chiplets, right? And so what are the two ways of making this kind of 3D transformer? So one is to do vertical laminations, and if you use a ferromagnetic material, right? So one is to make vertical laminations, and another is to make horizontal laminations. So if you do vertical laminations, you start with the substrate, you essentially dig trenches through it, you fill it with magnetic material, and then you fabricate a coil around it, right? In the second approach, in a vertical lamination case, you have to first put the coil and then you have to deposit multiple layers of magnetic material, insulator, and so on, right? Obviously, this is going to be easier than this. This is going to be easier in the sense that you don't have to make trenches here, but you can only make it so tall because you have to do multiple levels of lamination, right? But here, if you can find a way to etch these holes, high aspect ratio holes with good efficiency, then you can make this inductor in one shot, right? So we need to still figure out which is the best way to, once we have an optimal material and so on, we need to figure out what's the best way to make this transformer. And here is like some, PowerPoint way of we can integrate this transformer is to make this transformer chiplet essentially in silicon. So this would be like a high resistance silicon, and you have the turns of the coil in essentially made in that high resistance silicon with the magnetic material in the middle. And then you can use this as a chiplet, and you can bond this to the backside of, say, your SIF, as well as on the other side, you can bond like a other power conversion chiplets, like a rectifier. You still need a rectifier here, so you can add a rectifier, you can add controller.
So in this first one, core type 1, you're assuming that the substrate itself is the core, right? Material for the magnetic core.
No. Substrate is just air. I mean, it's just high resistance silicon. Then you plate the magnetic material.
Oh, you plate it, I see.
Yeah.
So, Professor T-Way, they just have a paper about cobalt TSV this year ECTC. Do you think like cobalt plating and cobalt, like filling the trenches you made with cobalt would be a ideal case?
Yeah. I mean, if there's a process to electroplate, right, the material through these fine holes,
Yeah.
then you won't necessarily use cobalt because cobalt is relatively, it's not very soft compared to like permalloy, like nickel iron or something. So you may have to use some of the alloy ferromagnetic material. But if there's a way that you can make these trenches and electroplate it, right, we can use the same process for some other material instead of cobalt.
Yeah, because when I looked at this, the first thing that came to my mind is the cobalt TSV.
Right. Yeah.
So, okay. So now at the backside, we will have transformer and rectifier and also some kind of buck converter as well.
Yeah, I mean, it can be placed here also. I mean, transformer can be here and power chiplet can be here.
I see.
But yeah, I was thinking of basically making the transformer as a chiplet, which can be directly attached rather than trying to build it directly on the SIF.
I see.
Because building it on the SIF, everything is going to warp. It's
Yeah.
going to have a lot of second order effects, right? But if we can find a process so fundamentally, right, we need to figure out a good materials, right? Once we have that and we have some optimized coil geometry with some material, then we need to think about how to make it, right? And I think the best way is to make it as a chiplet so that then you can use this for something else also. Need not be just for backside power delivery. Right?
I think the easiest to start with is actually ironically core type 2. Because but you have to, so one thing is we are kind of limiting ourselves to using only silicon-like processing technique, right? We don't use any packaging. Like, for example, you can make your wiring much thicker if you use like a PCB like
Yeah.
and you can laminate these here very easily, with polymer, right?
Correct.
So if you were to make this dielet with a polymer backend and then bond that transformer chiplet to this, that you may get a better result in my opinion.
Yeah, but we don't have that capability here, right?
Yeah, so it's like but you can spin coat, maybe not that.
No, see, but the issue with making it like this, right, is you can only make it so tall, and because the inductance depends on the volume, you see.
No, what I'm saying is you can make it tall because like for
example, okay.
PCB layers like hundreds of microns.
Okay, also one more thing, right? It really depends on the frequency. If you want to operate this at say 100 megahertz, right? These laminations are essentially going to be like 200 nanometers thick. So you have to end up using some deposition process, some some PVD process,
If
right?
there's some spin out dielectric, it doesn't have to be 200 nanometer. It can be like tens of microns.
No, but you want
magnetic
thin. No. You need thin laminations because you need thin lamination of magnetic material to reduce eddy currents, and you need the insulation to be as thin as possible so you can increase the fill fraction.
I see.
Right? Okay. So it has to be a thin film process. Okay. So that's why if you are using a thin film process to build this, you have to do so many layers, right, to get that volume. That's going to be a very expensive process. You have to do, remember, you have to do a metal insulator, metal insulator, metal insulator, one after the other, right? So imagine you're doing 100 layers of that, right? Imagine you're building like several microns of this, which each layer being just 200 nanometers. You may have to do this hundreds of times.
Okay. So,
But here you can potentially do it just one shot.
and how big does your substrate has to be?
Substrate need not be this thick. That's the
Yeah.
point, right? So
How big?
you can break this up into pieces and bond it. That's what I felt. It has to be several microns thick, like 2 microns or something. One or two
And
microns.
then you can use some, yeah,
But then you can
organic
just use the
material. Yeah. Sorry.
No, and then you can just use the first 2 microns, right?
No, but imagine
Yeah,
you are.
take it down to 4 micron. You can just use a organic.
Or you just make the first wiring layer, then deposit a 2 micron PCB layer, then dig the trenches in the 2 micron PCB layer to the top layer of wiring.
Yeah, but you have to do 2 micron.
Sorry. Did I say the inductor thickness 2 microns? I meant 2 millimeters.
2 million.
That changes things.
Okay.
Yeah.
Okay, 2 millimeter.
2 millimeters.
I see.
Yeah, obviously. 200 nanometers, yeah. 2 millimeters.
It has to be 2 millimeters thick total.
Yeah,
right?
yeah. Let's say 2 millimeters thick.
Then you can like 0.5, 0.5, 0.5, kind of bond it to it. Yeah, like 200 micron.
Yeah, that's what we are planning to do,
Stacks.
right? But again, like if you use some crappy magnetic material, it's just gonna be like bad.
But
Also, the thing is the plating of that material inside.
Yeah.
It's gotta be a platable material.
Yeah.
And do they have platable materials that are?
Well, you can plate alloy ferromagnetic, but like that's where also you need like because people have shown plating of cobalt, zirconium.
But TNT, I only see cobalt.
Yeah, that's what you have. Like you're extremely process limited with the materials you can choose.
Yeah, I
The
mean,
other approach, you're allowed to take whatever, anything that can be laminated. You know, that's your thing. So you have a much wider range of materials to choose.
then you need a way that you can maybe make the film separately and use some packaging way to laminate it.
That's what I was saying. Like you have to figure out, you have to do like a layer transfer to make
Yeah.
like basically, you know, some heterostructure of this material, right?
Yeah.
And then you have to just transfer that and then
Correct,
really
correct,
your foil and everything.
Yeah,
like that.
yeah.
But it has to be 2 millimeters, you said.
Yeah.
But what if the material is like, it always needs to be 2 millimeters, regardless of the material.
No, I'm not saying that, but I mean that we have to see. But
Yeah.
the thicker it is, the better it is per unit area.
No, that makes sense.
Okay.
Yeah.
That's also the reason why remember the Global Foundries inductor we saw, right?
Yeah.
The reason the inductance density is so bad because it's just one thin layer.
Layer, yeah.
Yeah.
They have to integrate on the back end, otherwise the stress would be too high.
Yeah. This will be a combination of doing like a kind of semiconductor process, but then will be integrated by packaging, like by bonding this die to wafer attached, right?
And you say from your simulation, like you are confident that it can do 48-1, like if you have a very thick transformer.
No. It's a materials. 48-1 is a materials problem.
I see.
So if you are trying to do this problem, right, what you need to do is we need to better our model first, okay, because we are doing simple analytical model, right?
Okay.
We have to do like an actual simulation model and then do a Monte Carlo with that. So, or some way to figure out what is the limits, right? Essentially find the limit of that curve that limits how well you can do. And then once you characterize that, you need to figure out, okay, what material innovation I need to reach the point I want, right? But yeah.
Okay, I think you should actually still focus on core type 2. I know it's coming back to that. The reason being is like, if you actually study what the exact thickness of that layers, all those layers need to be, you know exactly for the material that you had in mind.
Mm-hmm.
Do you know?
Oh yeah, for this frequency, right?
Yeah.
Typically the ferromagnetic thicknesses are like 100 to 200 nanometers.
No, I know that, but like if each stack, right,
Mhm.
and the specific height you need. Like
No,
know you want
I don't know that
just to
yet.
meet spec, because I feel like that's quicker to get started with in terms of. But the only thing is the lamination part. You got to figure out that.
Yeah, lamination also growth.
In the growth.
Yeah. Because
both are tough.
yeah, because this growth has to be done in the presence of a field.
Yeah.
Because you need to induce that crystalline anisotropy, right? So even if you're doing sputtering, it has to be done with an in situ. Like a lot of these people use setups where they have they essentially have this whole evaporator, but they have the evaporator sitting in a Helmholtz coil. Okay, that's like essentially an MRI coil generating very high magnetic field to create that kind of anisotropy. right? So yeah, like, you know, when I was doing this project for my master's, right, that's why essentially I kind of abandoned this because I saw this was like a very difficult problem, which we didn't have the capability anyway to do here. Yeah.
Yeah,
Yeah.
a lot of
Yeah.
cancer failure.
Yeah.
So you say currently your simulation is 4-1?
48-1. This is just a very simple kind of analytic model.
I see.
So this was all done by hand. You see, the calculations are all done by hand. And then the equations were used in kind of like an algorithm and then to generate the Monte Carlo.
So
But
okay,
it's the only takeaway from this is that even if you do a more accurate simulation, it's going to have these kind of trends. We need to figure out by doing more accurate simulation where the limits of this essentially this trend is. Right? I want to figure out what the bound is. So imagine I have the best material, right? Where is the bound of the best material I can do today, right? And then figure out in order to reach somewhere here, what improvement in materials I have to do. And then try to figure out what kind of growth or what kind of new alloy I can do that has that material problem.
This is like Haoshan's best ever get. And
Yeah, correct. Exactly. Yeah. Otherwise, it'll be just like any other inductor transformer paper, which is people just have some material, put it, they have very bad results, but it's still a paper. Right? It'll end up like that.
That's true.
But if you want to really solve this problem, right, I think you need to look at this from kind of this physics perspective with kind of modeling and then kind of fabrication. It's a big project. Like, I don't think one student can do this. Yeah.